Albert Einstein once said, "Anyone who has ever tried to present a rather abstract scientific subject in a popular manner knows the great difficulties of such an attempt. Either he succeeds in being intelligible by concealing the core of the problem, and by offering the reader only superficial aspects or vague illusions, thus deceiving the reader by arousing in him the deceptive illusion of comprehension, or else he gives an expert account of the problem, but in such a fashion that the untrained reader is unable to follow the exposition and becomes discouraged from reading any further." If these two categories are omitted from today's popular scientific literature, surprisingly little remains. But the little that is left is very valuable indeed. It is of great importance that the general public be given the opportunity to experience, consciously and intelligently, the efforts and results of scientific research. It is not sufficient that each result be taken up, elaborated, and applied by only a few specialists in the field. Restricting the body of knowledge to a small group deadens the philosophical spirit of the people and leads to spiritual poverty. Hello, my name is Thomas Yale. In this video I'll be discussing NLP, or Natural Language Processing, a subfield of artificial intelligence. As implied by Einstein's quote, this is no dry academic lecture, but rather a fascinating look into one of the most intriguing, long sought after, and elusive goals in computer science. This video addresses both professionals in this remarkable field and those who have either may have never heard of it, or otherwise knew exactly what it was. Natural language processing, or more specifically natural language understanding, is the attempt to enable computers to derive meaning from human languages such as English. However difficult it is to produce software that at least reasonably simulates human understanding of language, NLP is a reasonable goal, simply because language serves as the principal and undoubtedly easiest means of communication among human beings themselves. You can imagine how much more effective computers would be if they could interact and communicate with humans in the same way. There are many sub-goals in NLP, some of which already have real-world applications. In this video, however, I'll be addressing only a few of them, the ones that happen to be the most difficult. Part of speech disambiguation, in which a program tries to determine which part of speech applies to each word in a given sentence based on context. Word sense disambiguation, in which it tries to determine which definition applies to each word in a sentence, again based on context. Parsing, in which the program analyzes a sentence and determines its grammatical structure. Question answering, in which a program answers questions based on a body of knowledge it has acquired from previously entered sentences. And discourse analysis, evaluating a particular statement to determine whether it agrees or conflicts with any related statements in such a body of knowledge, and either reconcile or resolve any inconsistencies in the information. This is the same basic principle that information management systems use today, to acquire, organize, store, maintain, and retrieve information. The only difference in that language understanding NLP software would also require the ability to convert and display relevant outputs, no matter how it represents or stores it, back into grammatically correct English replies, or even its own questions, to the human user. For software like this to work, it would require four things. First, it would need a lexicon, essentially a large catalog reference of words in a language containing data on how each word is used and how it relates to others. Next, it would require a parser and grammar rules, both of which must be capable of separating sentences into individual words and phrases, so the software can deduce their structure and thereby determine what sentences mean. Lastly, to compare and evaluate a given sentence to others accumulated within a body of English language knowledge, it would need a reliable form of logic accurate enough to represent the whole range of real-world events and ideas. In essence, any statement, fact, assertion, opinion, belief, question, or speculation human language can express. This last item, the language logic, would be particularly important because we can express the same idea in a number of different ways, using a vast variety of different words in any combination within an almost limitless range of sentence structures. Without it, the program would be ineffective. For no matter what words are used, or what structure in which they're placed, one or more of which may be equivalent in meaning, the program would have to use the same expressions of this logic to represent it and, in effect, understand it in the same unambiguous way. As ambitious as this goal is, a whole host of problems have plagued natural language processing since its beginning, way back in the 1940s when computer pioneer Alan Turing established the engineering discipline we now know as computer science. The main difficulty is that humans have an ability that computer programs do not. An abstract capacity sophisticated enough to understand and accommodate the near-infinite range of expression in human language, allowing us to judge not only which series of words is grammatical, but also what meaning they convey through the grammatical structures in which they're used. The grammar of English or any other language is generative, meaning we can almost instinctively, seemingly with no effort whatsoever, construct sentences to express ourselves in nearly limitless ways. Linguist Noam Chomsky once called this ability making infinite use of finite meaning. From a biological perspective, the human brain is naturally programmed for language use. But in developing effective NLP, our own familiarity with our native language, no matter what language that may be, at once presents a formidable obstacle. It makes encoding this natural human ability into a computer program an immensely complex and seemingly impossible undertaking. To better illustrate this example, let's examine the simple sentence. The man gave his son the money. The dictionary can give us all the lexical meanings or definitions of the word man, but it can't tell us how the word man is used in the sentence. It could mean a species of Homo sapiens or other hominid, a piece on a board game, or man in the respect of humanity, all living human inhabitants on Earth. Moreover, the word man alone can be a verb, meaning to take charge of a certain job, occupy a certain workplace, or to provide a workplace or equipment with personnel. While man can have several definitions or lexical meanings, it can have only one grammatical or structural meaning within the context of this particular sentence. In it, man clearly means adult male. This is why grammar is particularly important in language. It enables us to derive the meaning of each word, the structural meaning, the meaning that the speaker or writer intends, by providing the necessary context with which to recognize it. But what basis would a computer program have for any given sentence to deduce the individual structural meanings of words? The answer is the lexicon, the word reference with data on how different words are used and relate to one another. However broad and diverse grammar can be, it does follow definite patterns. If a series of words in a sentence follow a certain grammatical arrangement we recognize as meaningful, we should be able to substitute one word with others, but in a way in which both the grammatical pattern and meanings of the other words remain unchanged. For example, the concert was good. The food was good. The coffee was good. The taste was good. The container, difference, privacy, movie, family was good. But this kind of substitution doesn't always work. Consider the difference between the sentences John is easy to please and John is eager to please. The first means that it is easy for someone to please John. The second, that John himself is eager to please others. You could still respectively apply word substitution and say John is difficult to please and John is anxious to please. But despite that all the substituted words are adjectives, the same grammatical structure can still convey two or more different meanings. What does this imply exactly? It implies that a lexicon supply of words must be separated not only by part of speech, but by addition criteria, separating still further into smaller sets of words. The reason to do so is clear. It is so that any sentence the program encounters, it can deduce the meaning of the structure based on whether a particular keyword, whether noun, adjective, verb, or adverb, belongs in one set or another. Let's take a look at a third example. The noun phrase, the shooting of the hunters. Are the hunters the ones doing the shooting, or are the hunters being the ones shot at? For this particular structure, to shoot obviously belongs to a particular set of verbs which remains ambiguous. But this set of verbs is separate from two other sets. The growling of the lions can only imply that lions are growling, while the raising of the flowers can imply only that someone is raising flowers. Each of these last two structures has only one meaning. It all depends on whether the verb used is in one set or the other. Let's take a look at yet another example that shows how this separation of words into different sets is necessary. Compare the following 5 sentences. The idea surprised me. The rock fell off the table. The celery was flourishing. The dog sneezed. The girl wrote out the check. Some verbs can be used with any subject noun. But look what happens when we transpose these subject nouns with different verbs. You can say the rock, celery, dog, or girl fell off the table, but you cannot say the idea fell off the table. You can say the celery, dog, or girl was flourishing, but you cannot say the idea or rock was flourishing. You can say the dog or the girl sneezed, but you cannot say the idea, rock, or celery sneezed. Finally, you can say the girl wrote out the check, but you cannot say the idea, rock, celery, or dog wrote out a check. This shows another clue to determine structural meaning. Only certain types of subject nouns can perform actions of only certain types of verbs. Yet another clue with which humans recognize structural meaning is what linguist Charles Fries called function words. Not the nouns, verbs, adjectives, and adverbs which may have multiple lexical meanings and parts of speech, but rather conjunctions, prepositions, irregular adverbs, and pronouns, which have only one part of speech. Granted, in English there is one exception. Nevertheless, this one exception is negligible since it doesn't prevent us from understanding the sentences that use it. Language has yet another saving grace. Apart from utterances humans often use in normal conversation, consisting only of subordinate clauses, prepositional phrases, or even single nouns, adjectives, and adverbs, is that no matter the number of words or number of ways in which they can be combined, all grammatically correct sentences can be traced back to and found to consist of a main subject-noun phrase and main verb phrase. S means the class of all sentences. This remains true whether the sentence is a statement, question, or command. If a software can structure real-world information as expressed in human language into computer-understandable data, what kind of logic could be applied to maintain that information? Which one would ensure or guarantee the highest possible degree of logical consistency within the information it accumulates, and reconcile any logical contradictions, however direct or indirect? Whatever the best logical system for NLP is, all logical systems must have consistency, where no expression in the logic can contradict any other; validity, where no false conclusion or inference can result from true statements or premises; completeness, where if an expression is true, it can be proven within the logic; and soundness, the reverse of completeness, where if an expression can be proven within the logic, it must be true. NLP programs have used various types of logic: traditional Aristotelian or syllogistic logic, propositional logic, mathematical logic, computational logic, dialectical reasoning, but with only partial degrees of success. Throughout the historical development of logic, each is proven to have certain shortcomings. None of them satisfy all the requirements logical systems must have to reflect what happens in everyday life. Yet the one type of logic that shows the most promise in representing and evaluating real-world events, especially when they're expressed through language, is modal logic. Let's look at an example of how modal logic expresses the sentence, "Some cat is feared by every mouse." The sentence is ambiguous. Does it mean that 1, for every mouse there is at least one cat the mouse fears? Or 2, there's only one cat that every mouse fears? Modal logic clears up this ambiguity. Modal logic accommodates propositions that are not only true or false, ones which actually or actually don't be or happen. It also accommodates propositions in other modes, ones that may or may not be or happen, must or must not happen, do not have to be or happen, or only sometimes, always, or can never be or happen, whether in the past, present, or future. Modal logic, however, has one setback. The number of logical expressions would be just as limitless as the number of sentences it could be used to represent. Which raises a question. What basis would a computer program have to generate the necessary modal logic expressions it would need, but still use the logic reliably enough no matter what sentence the user enters? It's simply not possible. The only reasonable alternative is to follow Noam Chomsky's principle stated earlier, to make infinite use of finite means. This would require a revision of modal logic to make it a closed system. This would enable a language understanding program to reach the greatest possible number of logical conclusions and implications from the smallest possible number of expressions, functions, operators, and symbols. With such a comprehensive, all-encompassing form of logic, the vast complexity and expressibility of human language could be represented with a finite set of formulas of profound simplicity. Such a goal is far from impossible or impractical. Consider the science of physics. During the 20th century, physics has progressed beyond mechanical experiments to the point where it is necessary to describe, represent, and predict all manner of physical phenomena and events with mathematical equations. Indeed, the aim of the practical physicist is to enunciate the laws of nature in ever more precise mathematical terms. More importantly, however, these equations work, and they establish a sound basis to explain any kind of phenomena, ranging from subatomic particles to black holes, phenomena which, at least for now, remain beyond the reach of our limited physical senses. Yet such a form of language understanding logic, even in the 21st century, does not yet exist. Even if natural language processing remains an engineering discipline and can't be classified as a true science, its future is not all bleak and hopeless. Two lexicons hold the key to constructing a fully functional NLP software with all the capabilities I've discussed so far. The first is WordNet, developed by the Cognitive Science Laboratory at Princeton University. WordNet groups together words into sets of synonyms, synsets for short, representing individual concepts, which in turn are linked together through lexical associations or associations of meaning, such as antonyms. We've all learned about synonyms and antonyms in elementary school, groups of words that have the same and opposite meanings. WordNet uses these relations too, plus many more. WordNet is the single largest lexical database in English, containing 149,178 words, each associated with all others within a network consisting of 117,597 of these relations. From the diagrams I've shown, WordNet provides immensely solid ground for the language understanding logic I've described, as well as the means for deriving the structural meanings of words in various sentence structures. For example, Tom endeared Larry with a board has a completely different meaning from Tom hit Larry with a board. Both have identical structures, but WordNet distinguishes between the lexical meanings of board so the right structural meaning can be derived. This it does by including the word board in two different unambiguous synsets or concept groups, board committee for the first and board plank for the second. Essentially, WordNet is a computer model which maps most, if not all, of the totality of concepts available to the human mind. The other is VerbNet, developed by the Institute of Cognitive Science and Linguistics at the University of Colorado at Boulder. VerbNet organizes 6,818 English verbs, all of which are defined in 8,419 different ways, into 270 different classes, with each class listing a set of sentence structures in which certain sets of English verbs are used. For each sentence structure, VerbNet provides a syntax, the structure itself, including a description of each kind of word it uses, and the semantics, an expression of one or more logical predicates. This expression describes the event or idea the structure is supposed to convey, given the limited subset of verbs it can use. The fact that these semantic expressions are expressed with just a handful of predicate types, and an even smaller set of arguments, is particularly important. They provide the limited, finite set of symbols for the language understanding logic that the program would require. Yet this pairing of syntax and semantic notation not only provides a way to formalize a language understanding logic, but also provides a solution to the problem of distinguishing between identical structures with different meanings. Otherwise, the NLP program would be unable to recognize the difference between sentences like, "She called me a fool," and "She called me a taxi." You could compare the process of disambiguating parts of speech, deducing the part of speech of each word in a sentence based on context, to a lottery game using a set of numbered balls. The more balls there are, the more possible combinations there are, and the less chance of winning on a random set of numbers. An even better metaphor might be a bank robber facing the challenge of opening up a peculiar kind of bank vault. The combination lock has only 4 digits on the dial, but the vault has a combination 20 or more digits long. This amounts to 1 trillion possible combinations, and leaves the robber with the horrible problem of testing each one, at least until he figures out which one opens the safe before the police arrive. I predict a long prison term. While working on my own software called Discovery, I face the same problem of probability. Any one word could be a noun, verb, adjective, or adverb, or any combination of the two, or 3, or sometimes all 4 as in the case of well. For Discovery, the problem of deducing the right part of speech for each word in sentences 20 or more words long was even harder, even with the basis of what constitutes correct grammar. I solved this problem of contextual part of speech disambiguation 10 years ago. Instead of rushing headlong into programming it to test all possible part-of-speech combinations of any sentence the user might enter, however, I did what any sensible person with an intractably huge job would do. Break it up into far smaller, more easily manageable jobs. I programmed Discovery to separate any sentence entered into it into segments, separated by the words Charles Fries called function words, the conjunctions, prepositions, irregular adverbs, and pronouns which have only one part of speech. Then I tested each shorter segment from a list of segments that actually occur in grammatically correct English sentences. The segments that matched ones in the list were retained, while all the rest were eliminated. The result was a potentially astronomical number of part-of-speech combinations for the entire sentence reduced to a very few, and in some cases, only one. Even if Discovery determined only one combination is valid for any randomly entered sentence, its job didn't end there. It still had to diagram it. We've all learned how to do this in elementary school, by which all grammatically correct sentences consist of a main subject-noun phrase and main verb phrase. Given the generative nature of language, the main subject, verb, or both may consist of a whole slew of adjectives describing nouns, adverbs modifying verbs, prepositional phrases specifying place, time, possession, origin, destination, as well as an enormous variety of relative clauses and subordinate clauses that, independently, can be represented as separate sentences by themselves. To get from this ground-level plethora of grammaticality and ascend to the summit of the main subject noun and main verb phrase, I separated this second huge job into a series of smaller, more manageable ones. I programmed Discovery to run any remaining part-of-speech combinations for the given sentence through 8 different levels of grammar rules. Again, Discovery regarded any combination that didn't pass through all of these stages as grammatically incorrect and eliminated them, until it reached that one combination that conformed to its entire framework of grammar. This may sound like a long, drawn-out process, and granted, it was an arduous algorithm to write programming for. But once written, Discovery was, and still is, capable of disambiguating and diagramming nearly any given English sentence of 30 or more words in less than 1 second. Faster now, since computer processing speed has multiplied many times over in the last decade. But even if the problem of part-of-speech combination by context is solved, still another remains, the problem of combination of all the senses or definitions a single word can have. Even if a lexicon provided all possible senses or definitions for any word, it wouldn't matter if you knew each word's part of speech in a given sentence. You would still have the same problem. Too many combinations to test, and no basis to know which combination is the right one. Solve this problem, and you would have the basis for reliable NLP software with the capability to understand and learn from English text. In my work on Discovery, this problem has remained unsolved for the last 10 years. Until now. I believe the complete integration of WordNet and VerbNet, which has not yet been established, provides the means to solve the long-standing problem of word sense disambiguation and thereby elevate natural language understanding to the level of science. I illustrate this in my final example, the generic sentence, "The quick brown fox jumps over the lazy dog." WordNet provides the concept hierarchy through additional syntaxes for the verb to be to restrict certain types of adjectives to modify certain types of nouns. In this case, only the definitions for behavioral attributes of quick and perceptible attributes of brown can apply to the definitions for people and animals denoted by fox, in addition to other types of semantic constraints to exclude inapplicable definitions. Definitions for each word in WordNet, moreover, are ordered according to the most commonly used to the least commonly used, limiting the combinations of lexical meaning to a very few, if not one. Beyond the larger context of a conversation, the more common animal definition of fox most likely applies. Likewise, the same constraint dictates that only the behavioral attributes of lazy can apply to the definitions of people and animals denoted by dog. Again, outside the context of a conversation, the more common animal definition of dog most likely applies. Still further, the association of syntax elements in VerbNet sentence structures used singly or in combination for more complex sentences. Given also VerbNet's selectional restrictions on structural elements and syntaxes associated with parent synsets in WordNet to further eliminate inapplicable possibilities of lexical meaning, can more reliably confirm the structural meanings of all words in any given sentence. What you see before you is the grand aim, the ultimate goal, the holy grail by which computerized natural language understanding, for which computer engineers have striven for the last 70 years, can at long last be accomplished. I have genuine respect and admiration for the academians and graduate students for their formal education and their years of dedication in acquiring it. particularly since I as well have done as much. Otherwise, landmark accomplishments such as WordNet and VerbNet would not exist. Yet formal education can often straitjacket one to think along lines of inefficient, sometimes unworkable solutions. In consequence, it can often pose barriers to the formation of new, innovative, more reasonable and workable solutions that only a liberal education can provide. Judging whether my solutions are good or bad at first glance is not only premature, but irrelevant. Once implemented within the software, those solutions will either work or they won't. Moreover, I may be only a lowly temporary staffing clerk, but be fair in your assessment and let no prejudice betray you. After all, when formulating the special and general theories of relativity, Albert Einstein, widely regarded as the greatest scientist of the 20th century, was but a lowly desk clerk working in a patent office. I don't deny my own education in NLP has a few holes. I may have only an associate's degree in computer technology. I ask you, however, to look not upon my academic status, but instead upon the efficacy of my methods. Abdu'l-Baha, one of the central figures of the Baha'i faith, commented more poignantly on this matter. He said, "The fact that we imagine ourselves to be right and everyone else wrong is the greatest of all obstacles in the path towards unity, and unity is necessary if we would reach truth, for truth is one." Everyone has the potential to contribute. Everyone has the ability to collectively engender the creation of new insights, possibilities, opportunities, and ideas that no single one of us can arrive at alone. Everyone. No member of the human race is an exception.